It's my pleasure to welcome Branimir Ćaćić to our seminar this week. And he will talk about differential Cuntz Pimsner constructions, variations on a theme. Take it away, Branimir.
Thank you very much, Karen. So I think there should be hopefully something of interest to everyone in this talk, but I have no idea if it will be actually pleasing to anyone, but let's give it a shot. It's work under that's being sort of heavily sort of written up, so it may get a little messy at times. So what is going on? Basically, I want to persuade you that you can take the Kuntz-Pimsner construction in the case of Morita autoequivalences that you all know and love, and that you can distill it down to some abstract nonsense. But by doing so, you can then take the Kuntz-Pimsner construction and actually adapt it to non-commutative differential and Riemannian geometry. So in terms of the non-commutative Riemannian geometry, in the interests of time and in all sorts of meanings of the word, I won't be able to really talk about spectral triples in any detail, but I'll indicate some things that will hopefully be of interest. So the basic idea is I want to talk first about how you take the Kuntz-Pimsner construction you know and love and pare it down to its sort of category theoretical essentials. Then I want to talk about how you can sort of get a sort of differentiable Kuntz-Pimsner for basically horizontal lifts of differential calculi on the base in terms of covariant derivatives on the associated lines. Then I want to go further and say, okay, let's say we actually have a full-on quantum principle bundle with a full calculus and everything. To what extent do we still have some sort of notion of differentiable Kuntz-Pimsner construction? And I'll show that we do, and that we actually learn something from it. And then finally, I'll start indicating be able to say enough to indicate the limitations of the spectral triple formalism as they relate to quantum principle circle bundles. And in the process, I'll quickly indicate that the central role of this notion as generalization of this notion of metric continuity that was first observed by Belisa, Marcoli, and Rehani. So if I probably won't have the brain energy to see the chat, but if anyone has any questions, please, or Rotten Tomatoes, please interrupt me as required. All right. So what's the abstract nonsense that's at the heart of everything? Well, at the heart of everything is actually a fairly straightforward sort of categorical generalization of the notion of group. It goes all the way back to a PhD student of Grothendieck called Sin. And then there's various sort of iterations of defining the notion. Laplace had a huge role in getting the theory down to something manageable. And then Baez Lauda have a really beautiful paper where they write up a lot and sort of give a really nice presentation of these issues. So basically, we're going to take a group. And instead of just having the group elements, the group law, and the unit, and everything holding the nose, we are going to replace the group elements by objects in a category, the group law by monoidal structure, and the inversion by some sort of reasonable family of arrows. And then, and then what you have is that this notion that a group element times its inverse is equal to the identity, we'll promote that to the existence of an arrow. So a coherent two group G consists of a monoidal category where every arrow is invertible. So this is the most abstract sort of setting where you can talk about just a tensor product with an idea of a unit that, such that when you tensor product something with that unit, you're isomorphic to the thing you started with. We'll have, to be deceptively simple, we'll have some sort of map from the objects, from the class of objects to classes of objects, which we'll call monoidal inversion. And it'll take an object G to an object bar G. And then we'll have a family of arrows. So for each object G, we'll have an arrow from bar G, tensor G, to the unit. We'll call this distinguished arrow the evaluation of the object G. And so what we have a monoidal inversion, monoidal inverse chosen for each object, and we have an evaluation map chosen for each object. So obvious example, the most elementary example is that a group gamma automatically defines a two group. You take your category will just be the underlying set with just the identity arrows. It's called a discrete category. You get a strict monoidal structure given by the group law. So strict means that all your associators and unitors and whatnot are actual literal identities. Monoidal inversion is given by inversion in the group. And evaluation is just given by, gamma inverse times gamma equals 1 on the nodes. So this laundry list of conditions looks pretty innocuous. It actually looks pretty weak, but it actually packs a punch. There's a theorem due to Laplace that basically says the following. Here I haven't said that monoidal inversion is a functor, but it actually extends uniquely to a functor in such a way that makes the evaluation, so the family of evaluation maps into a natural isomorphism. And then from then on, you automatically get your two zigzag identities and a whole lot of stuff builds up. But there's actually even more to the story, because what I want to emphasize is that coherent two groups have a beautiful and powerful coherence theory. So that's what I want to get to next. So before I continue, are there any questions? Okay. So what do I mean by coherence? Well, if you have a coherent two group, you can take all these sort of basic structural arrows, the identities, the left uniters, the right uniters, the evaluations, the associators, and then you can you can generate a family of arrows from these things via finitely many applications of composition inversion, monoidal inversion, and the tensor product. You can think of these as your elementary arrows. They are generated purely by the given structure of your coherent two group. So it turns out that there is a coherence theorem along the lines of Maclane's coherence theorem for monoidal group categories that applies to coherent two groups. There's a first iteration due to Ulbricht, and then it was really beautifully finessed by Laplace. And what it says is that between any two objects in a coherent two group, there is at most one elementary arrow between them, from the one to the other. And so now this means that anytime you can write down a diagram in terms of elementary arrows, boom, it automatically commutes. So this is pretty awesome because it applies, already one rather important thing. So for those familiar with bar categories in the sense of Bex-Magid, I think there's also an equivalent definition due to a guy called Egger or something like that. Let G be a coherent two group, then basically you can uniquely turn G into a strong bar category by means of elementary arrows. So a coherent two group is a strong bar category for free. Of course, here's a sort of interesting exercise that'll become all the more sort of transparent in its nature in a second. Suppose for those of you familiar with strong bar categories, think about what it would mean. Well, let me not get ahead of myself. It'll make more sense in a second. So groups are coherent two groups, but I want to get to something a little more interesting. So let's remember our familiar friends, the Hermitian line modules. So in this talk, I'll want to be able to maximize the sort of interplay between the sort of algebraic non-commutative geometry and the functional analysis, the operator algebras, the K-theory, the spectral triples, etc. So I'll always be talking about unital pre-C-star algebras, but I'll be doing so in such a way that absolutely minimizes the analysis as all humanly possible, but still packs a maximum, sort of optimizes for analysis without invoking analysis. So let me give the following relatively restrictive looking definition of Hermitian line module that nonetheless is what you get in pretty much any example of interest you can think of. So suppose it B is a unital pre-C-star algebra. Then we can define a Hermitian like a B module to be, as usual, a right pre-Hilbert B module E, equipped with a star isomorphism from B to the adjointable endomorphisms of E. You can do this even without topological completion. That satisfies the following. On the one hand, it has, in the sense of the unbounded KK theory literature, a finite frame, E1 through EM, which means that for any E and E, there exists some, you have some M tuple of elements, E1 through EM, such that for any E in capital E, you can decompose E like this. And then on the other hand, so you can think of this as a frame in the sense of the unbounded KK3 literature first.
Quick question.
Please.
This is EI times EI.
Oh, that's a type. This
should be E,
second guy should be E.
Yeah. Okay.
Yes.
Okay.
The second guy should be E. Yes.
Yeah.
So you can think of this as a frame, but then you also want what you feel like a co-frame. So you want some tuple, n tuple. Doesn't have, n doesn't have to be equal to m. These things don't have to have any relationship to these things. Some n tuple, epsilon 1 through epsilon n, such that 1 is the sum from j equals 1 to n of epsilon j, epsilon j. So this first condition implies that you are, in particular, that you're finally generated projective, and the second condition implies that you're full. But now what's nice is that if you can now form the conjugate, a Hermitian line module, quite readily, and this combination of sort of conditions means that everything just works out as you'd expect, and in particular, you can define the Hermitian the inner product on your conjugate module by this formula here. So it's everything that you expect, except I impose this relatively strong condition that's nonetheless what you find in all the examples. And I want to emphasize that at no point do you ever need a specific choice of the EIs or a specific choice of the epsilon J's. Anytime you use them will be in such a way that the end result is independent of the choice you made. So we're not going to be talking about specifically Grassmann connections or anything like that. It's really sort of, it's a sort of coordinate invariant thing where you can work in coordinates if you need to, but then the end result doesn't depend on the choice of coordinates.
Wait, I have another dumb question. Why is this a line module? Like, is it clear that it's invertible?
Yeah. Yes. That's the next slide.
Okay.
That's the next slide. It's not actually it's not an obvious thing, but this combination of things will give you what you want. So this is the next slide actually. That you get a Picard 2 group. You actually get a coherent 2 group, where an object is one of these Hermitian line modules. An arrow is a unitary, left and right bilinear unitary. The tensor product is the usual or tensor product of Hilbert-C-star modules, and the inverse of an object is its conjugate with this evaluation map. Those two. So what actually ends up happening? That combination of. So basically that combination of this 1-2 punch is actually quite powerful. And
I don't see how that 1-2 punch is not just, I mean, this would hold for any vector bundle of rank n.
It's the fact that this is a star isomorphism. The left action is a star isomorphism.
Aha, yeah. Sorry. Okay, yeah. I agree. Okay.
So it's a 1, 2, 3 punch. Sorry, no, it's a 1, 2, 3 punch. This is you're absolutely right. Without this is nonsense. This is a supreme importance. This is a supreme importance. And this, if you like, is behind the scenes. This is equivalent to the existence of a this is your co-evaluation in disguise. So these highlighting these things is not really working. This combined with these two things gives you a coherent 2 group of Hermitian line modules. And the whole point of dealing with a coherent 2 group instead of just the usual group of isomorphism classes is that we want to do differential geometry. We need to know things on the nose, or at worst up to explicit isomorphism. You want to talk about gauge transformations. These are going to be automorphisms of some kind. You need to know what the automorphisms are. You need to know things on the nose. So that's why we need to start thinking about coherent 2 groups as opposed to just the Picard group of isomorphism classes. So this is sort of one of the talking points for today. So now building up to talking about, if you like, principal U1 algebra, sort of your topological quantum circle bundles, we need to be able to talk about, in particular, homomorphisms from the group Z into a coherent 2 group. We want to be able to talk about the powers of a line module in a consistent, coherent way. And what the idea is that we should be able to stack them up to get your usual Kuntz-Pimsner construction. So you can make sense. So you can make sense. I mean, more generally, you can talk about a weak monoidal functor between monoidal categories. A homomorphism in simplicator between subcoherent two groups is just a weak monoidal category. So what do you have? A straight up homomorphism in the simple case where you have a group and a coherent two group looks like this. You have a function taking elements of the group to objects of the coherent two group. You have an isomorphism of the, you don't require F to take the identity of the unit of gamma to the literal unit of the monoidal category G. You just need there to be a nice little arrow, F super 0. And then you basically need, if you like, sort of, it's too much to ask for F to be literally on the nose, some sort of strict homomorphism, where F of gamma 1 times gamma 2 is F of gamma 1 tensor F of gamma 2. It's enough to have a family of arrows like this, and everything satisfies certain coherence diagrams. So this is look at this as just a bare minimum to guarantee that things work out nicely. So you have a homomorphism up to certain nice arrows that satisfy coherence diagrams. But this is something I've been struggling with for several days recently, wasted a lot of time. Even though a coherent two group naturally defines a strong bar category, if you want to talk about star algebra, stacking up Hermitian line modules and getting a star algebra out of the thing, you do need a finer notion of homomorphism. So this now takes us to a notion of Beggs-Magid. So basically what we need, we need to really be careful about how a homomorphism from a group to a coherent two group interacts with monoidal inversion. On the group, you have a usual group inversion, group element inversion. On the coherent two group, you have this monoidal inversion bar, which you can think of in the case of Hermitian lines as taking a line module to its conjugate. And now what do we need to do? We need to make certain, well, there's basically a unique candidate for an arrow from each F gamma bar to F sub gamma inverse. But what isn't so obvious is that these identifications satisfy some bare minimum of coherence axioms. So there's some coherence diagrams proposed by Beggs-Magid, and these do the job. It would be interesting to see if you can sort of simplify these things down, but that's a story for another time. So you may be thinking to yourselves, what the devil is a bar homomorphism from a group to a coherent two group? But there's one important example that you've been dealing with all this time. So let's suppose that B is a unital pre-C-star algebra. Then we can define an injective bar homomorphism, tau, from the star automorphisms of B to this Picard two group of B as follows. So what do you do? Well, on objects, what are you doing? You're taking an automorphism phi and just defining the right twisted line. You take the trivial line twisted on the right by phi. Nothing you haven't seen before. In particular, when phi is the identity, you've done literally nothing, so you can just take the identity. And then, well, here's the thing. You want to say that this is a group homomorphism, but it won't be literally a group homomorphism. This tensor product will not literally be this, but that's okay, because you have an obvious arrow. And in the same way, the conjugate of a tau sub phi will not literally be tau sub phi inverse, but that's okay. There's an obvious arrow. And so this is, if you like, the injective bar homomorphism that underpins cross products. So now what I'd like to do is basically, crudely speaking, I want to take Quantz-Pimsner and factor it into, I want to split it up in a certain way, into two pieces. One part is some sort of orbitwise Tanaka-Klein, and another part is the ability to take a bar homomorphism from Z to in particular Picard group, and say that it is uniquely generated up to natural isomorphism by the degree 1 guy. So this is so to do things in a sort of categorical fashion, in order to be able to talk about automorphisms, gauge transformations eventually, et cetera, we need to mind our morphisms. So now we can talk about morphisms between bar homomorphisms, and basically we want to talk about natural isomorphisms between these bar homomorphisms satisfying certain coherence conditions. So nothing super duper exciting. So it's ultimately a family of arrows, an arrow from a bar homomorphism R to a bar homomorphism of S. Bar homomorphism S is the family of arrows phi sub gamma from R sub gamma to S sub gamma that satisfies the appropriate coherence diagrams. And a thing to note, if you're just dealing with groups, everything just boils down to the usual homomorphisms. And so you just end up with the discrete category on the actual literal set of group homomorphisms from gamma 1 to gamma 2. There's just everything's strict, there's nothing to do. Okay. So this lets us basically isolate what I'm calling an abstract Pimsner result. So proposition, really trivial warm-up exercise for an undergraduate introduction to groups. If G is actually a group, then evaluation at the unit of the group defines a bijection from the homomorphisms from Z to the group itself. This is simple. What isn't quite so simple is the analogous statement for bar homomorphisms from Z to a coherent 2 group. But this turns out to be true. And it's morally already present in Brzezinski and Ricci-Kadlandi, but you can work it out at the totally abstract level of coherent 2 groups. And what you find is that there's a deformation retraction. You take if you consider the functor from the bar homomorphisms from Z to G, given by evaluation at the unit of Z at 1. Sorry, the generator. Sorry, good lord, not unit, generator. Then there exists basically a really nice quasi-inverse. You can go the other way. Basically, you can take any reasonable inductive scheme for producing the powers of an element of your coherent 2 group G, and as long as everything's done in a way involving elementary arrows, everything works out. This gives you this demonstrates this functor as a deformation retraction. So this composition is the identity. This composition is naturally isomorphic to the identity. So in other words, one of these bar homomorphisms is uniquely determined by its value at 1, and conversely, any element of the object of the coherent 2 group uniquely generates a homomorphism up to natural isomorphism, and that's good enough for practical purposes. Everything being the same up to natural isomorphism is good enough for most purposes. So, what does this have to do with the usual Cuntz-Pimsner construction? So again, super sort of odd-looking definition, but we can really finesse things using results of Ricci-Kadlandi and Ricci-D'Andrea-Landi. Suppose that B again is a unital pre-Cester algebra. Suppose now that P is a unital pre-Cester algebra with a U1 action. And let's define its isotypical components in the usual way. We'll say that P is a principal U1 pre-Cester algebra whenever P is the direct sum of the principal components. And you have the following condition, and this is something finessed by Ricci-Kadlandi. It's a strengthening of something finessed by Ricci-Kadlandi. On the one hand, there exists E1 through EM in P1, such that 1 can be written in this way. And on the other hand, there exists F1 through Fn in P1, such that 1 can be written in this way. And now Ricci-Kadlandi tell you that this implies that that you're strongly Z graded, et cetera, and everything works out. And you've seen something like this before, because if you consider the familiar friend SQQ2 with the usual generators A and C satisfying A star A plus C star C equals 1, and AA star plus Q squared CC star equals 1. Well, what you have here, you can take E1 equals A and E2 equals QC. And what you have here, you can take F1 equals A and F2 equals C. And for those of you who think about local triviality dimension, stuff like that, note again, I'm not presupposing any relationship whatsoever between any particular choice of the EIs and any particular choice of the FJs. They just need to exist completely separately. And one other thing, in terms of this condition and the analogous one for Hermitian lines, the moment that in the one hand B is a Fréchet C-star algebra dense under the, it's closed under the holomorphic functional calculus, and the moment the same thing is true for the U1 invariance here in the appropriate sense, then you can use the holomorphic functional calculus to weaken this considerably. Any questions before I move on? Okay. So what's the point? We can now, we can now start talking about basically the principal U1 pre-C star algebras over a fixed algebra B, which means that we consider a groupoid just category with invertible arrows. I'm not talking about groupoid C star algebras, just the naive thing. We'll take objects to be a principal U1 pre-C star algebra together with an identification of B with the invariance. And we'll take arrows just to be the appropriate U1 equivariant star isomorphisms intertwining respecting the appropriate structure. So this should be iota sub Q. No, this should be iota sub Q. This should be iota sub P. And so what's the point? Well, we can now start systematically talking about association of associated line modules to a principal U1 pre-C star algebra. And how does that end up working? Well, up to fussiness, literally all you do is just take the isotypical components and apply the appropriate sort of change of scalars given by this identification of B with the U1 invariance. And then what's nice is that you actually do get a bar homomorphism. And the point is that even though, and the point is that everything in principle could be non-trivial. This identification, this guy here is given, this map here is given by this given identification. And what these arrows encode is actually the multiplication in the arrow and the algebra P. And what these arrows encode are the star operation of P. So so the fact that you have a bar homomorphism with all these extra bells and whistles, those extra bells and whistles actually encode important information, critical information. And so what you actually find, it's a kind of orbitwise Tanaka-Klein, as a sort of warm-up, that you can, that association of associated line bundles has a weak inverse. Basically, the moment you have one of these bar homomorphisms, you can stack them up and get a principal U1 pre-C star algebra over B. And everything works out nicely like this. The one subtlety is the analysis here, and that's in particular where Abadi Iwas Excel and Arichi Kadlandi come in, because I've been asserting that we're dealing with pre-C star algebras with isometric U1 actions, so that there is a bit of analysis coming in here. So for example, already, suppose we have an automorphism phi. Suppose we consider the bar homomorphism given by taking the powers of phi and then applying tau to get those twisted trivial lines. What does this correspond to? What does it stack up to? This stacks up to usual algebraic uncompleted cross product with the gauge action. Another example to have in mind, you can think of SUQ2 as a principal U1 pre-C star algebra over Podlish, the usual Podlish, not equatorial or anything fancy. I'm not sophisticated enough for those things. And the thing to note is that this association of line modules recovers the canonical relative line modules over Polish. So you've been dealing with these things in mathematical lives. And so at the end of the day, forgive the cliche, you can piece it all together and recover the usual Cuntz-Pimsner construction that you all know and love. Cuntz-Pimsner specifically for Morita autoequivalences. And basically the idea is that any principal U1 pre-Cester algebra is uniquely determined up to natural isomorphism by this sort of associated line of Chern number -1 or whatever convention you want. And conversely, any line here generates, by taking powers, a unique principal U1 pre-Cester algebra up to natural isomorphism. And all that naturality means that you can talk about automorphisms, you can talk about, if you like, naive topological gauge transformations. So, for example, we have this sort of sanity check here. And then in terms of SUQ2, you can think of OQSU2 as generated by the relative line module over Polish generated by those generators A and C. So this recovers things you already know. Okay, so this is warm up. Now I actually want to start talking about differential geometry. So are there any questions before we move on? Okay. So now let's take our unital pre-Cester algebra B, our fixed base, and let's equip it with some differential calculus. Let's give it a star differential calculus omega B. Now, standard definition, you can make sense of a Hermitian. You remember that E is in particular a right Hermitian B module, a right pre-Hilbert B module, so you can make sense automatically of what a Hermitian right connection is. And so if you don't object too vociferously to this kind of Sweedler-esque notation, you can write down the two conditions like this. And so, nice little sort of, it's there in Biggs and Majid on quantum Bianchi identities, but I guess has some sort of prehistory. You can take a Hermitian right connection on a Hermitian line B module E, in particular, just a right Hilbert B module, pre-Hilbert B module, and uniquely extend it to a linear map like this. Takes e-valued forms to e-value forms of 1 degree up, satisfying this extended right Leibniz rule. So, as a bunch of people in the Prague group have been thinking about recently, where things get really interesting is when you remember that that this line is actually a bimodule, and you want to think about connections that actually see that left module structure and respect the left module structure in a suitable way. And so here's a mild riff off of stuff worked out by Biggs and Majid in their quantum Bianchi identities paper. Let's say that a Hermitian line connection on a Hermitian line B module E is basically a suitably nice bimodule connection. So what does this mean? Well, what we want to do is view the E-valued. We have two ways of constructing a notion of E. Since E is a B bimodule, we have two ways of constructing a notion of E-valued forms on B. What we want is an isomorphism of these two notions, a B bimodule graded isomorphism of these candidates with these candidates that restricts to the elementary, that restricts to the identity on E in degree 0. That now makes however you slice it, makes these E-valued forms on B integrated omega sub B bimodule via this formula. And now that we have the structure, we can now require that a Hermitian right connection satisfy a left Leibniz rule as well. So I've really sort of digested a lot of much more sort of generally framed conditions, phrase conditions in Biggs and Majid. And so now, if you have a Hermitian line connection in this sense, then you have then boom, you can define its conjugate. Where again, I'm writing things in terms of this sort of Sweedler-esque notation now on the left. So the heart of the matter is that this is now, let me pause share for a second. multi-factor authentication for the win. We can now take these things. The point is that we can now take these things and produce a souped up coherent two group of Hermitian line bimodules with Hermitian line connections. And luckily for me, again, Beggs and Majid have done all the hard work. We can make sense of the differentiable Picard two group of B with respect to this fixed calculus. It's a coherent two group. Objects are now Hermitian line modules with fixed Hermitian line connection. Arrows are arrows of Hermitian lines, these unitaries that intertwine the connections. We can, since we have this bimodule structure, we can define tensor products. This is a crucial insight of Beggs and Majid. And now we have a notion of monoidal inversion given by the conjugate connection, bimodule Hermitian line connection on the conjugate Hermitian line. And then everything else is induced by the usual Picard two group. So in particular, the unit is just the trivial line induced by the calculus on B itself. So working with this coherent two group is now going to be the heart of everything. So this is where we start seeing something new. So for example, if you're not only interested in topological automorphisms, but differentiable automorphisms, you can talk about those automorphisms of B that look to automorphisms of the entire differential calculus. And now you can refine our friend Tau, this association of these sort of twisted trivial lines to the differentiable level. And excuse me. Sorry about that. So what do? We need to take our usual trivial twisted line and equip it with a bimodule structure. This generalized braiding, as it's called, and with a covariant derivative. The generalized braiding can be simply written down like this. The differential can be written down like this. And the thing to observe is that these are less trivial than they look, especially this first one here. And we'll see that this first one here will become very important later on with respect to the notion of metric equicontinuity. The moment you try to think about spectral triples in analysis, these things here will become of supreme importance. Okay, and then everything else is just inherited from before.
Branimir,
yes.
I have a question. When you say generalized braiding,
yes.
Is it a real braiding in some
category? No. I presuppose nothing.
Okay.
It is just this. It's just this.
Okay.
I have no idea where this B comes from. This is the only structure I'm presupposing. So I in some of the relevant papers, the word generalized braiding is used, so that's why I'm using it. But I'm not presupposing it actually comes from any kind. Nothing is presupposed to come from any kind of braided category, braided tensor category. So it's just this bimodule structure. But in examples related to your quantum flag manifolds, then these are going to be profoundly related, as I guess Karatenuto and Wakula observed, as Alessandro and Ray observed. Very, very recently, in the context of your quantum flag manifolds, these things are intimately related to this Takuchi something, of which I'm blissfully ignorant, I'm afraid, to my discredit. So, okay. So now we can start piecing things together. Let's first start by just formalizing the notion of taking a differential calculus on the base and horizontally lifting it. So we presuppose nothing in the vertical direction, but even without knowing what's happening vertically, we can still talk about a horizontal lift of the calculus on the base. And so let's define a horizontal calculus for a unital principal U1 pre-C-star algebra over B to consist of the following. It'll be a U1 equivariant star differential calculus over P, omega sub PH for horizontal. We'll have an identification of the forms, the differential forms in the base with the U1 invariant form, horizontal forms, which we were given. And when we restrict our differential calculus to the U1 invariant horizontal form, we recover the differential calculus on the base. So it's really a straightforward U1 equivariant lift. And what's striking is that this doesn't look like it's saying much, but there's a nice lemma in the book of Beggs and Majid by which basically this subsumes the strong connection condition in a subtle, it really does. And now for the purposes of bookkeeping, we can form the obvious sort of category with invertible arrows. An object will be a pair of a principal U1 pre-C-star algebra with a horizontal calculus, and then an arrow between these objects will be an arrow of the unit of the principal U1 pre-C-star algebras that extend to the horizontal forms and that intertwine, basically to define an isomorphism of the horizontal calculi. So why do we care? We care about this because this will have a sort of horizontal differentiable orbitwise Tanaka-Kain that will relate homomorphisms from the integers to our differentiable Picasso group to these things here in a precise fashion, just like before. So this is where things start getting a little interesting. This is where we start making structural connections to unbounded KK theory. You can now define your association of Hermitian line modules with given Hermitian line connections in the following way. You basically restrict to the the isotypical components and just mind your P's and Q's in terms of this identification, the relevant identifications. And what's nice is, so the thing to note here, I'm invoking, so for each K, into each integer K, what am I getting? I'm claiming I'm getting a line module, Hermitian line module over K. And I'm claiming that I'm getting a Hermitian line connection on that isotypical component. So what am I doing? I'm basically taking the restriction of the horizontal derivative. This is a typo. I'm taking the restriction of the horizontal derivative. This should be this dph, serves me right for changing notation at the last minute. This is this dph. This is omega ph. This is your dph. You can take the restriction of your horizontal derivative to the degree k isotypical component and recast it as a Hermitian line connection. To do so, you need the existence of one of these frames, but this is in effect a frame for the line curly L's of P sub k, but you just need to know that it exists. This is independent of any choice of the E subject I's. And ditto here, you want to form the relevant generalized braiding. Again, it's a shell game involving these things. And the nice thing is that this is actually independent of any choice of this frame. And now you can induce all the extra structure you need for a bar homomorphism from this identification you started with of the U1 invariance of the B, from the multiplication in this graded star algebra of horizontal forms, and from the star operation in this graded star algebra of forms. And so now we have an orbitwise Tanaka-Kain theorem. Basically, this association of Hermitian lines with Hermitian line connections is an equivalence of categories. It's an equivalence of categories, and you can you with the of these principal U1 pre-C-star algebras with these bar homomorphisms, taking an integer k and spitting out the associated line module of Chern number minus k. This is an honest equivalence of categories, and you can go the other way basically just by stacking things up. And so, for example, if you take the powers of a fixed differentiable automorphism B and feed that into this, this should be tau hat, and then stack them up, you recover the trivial differential calculus on the cross product with where you have a flat connection on each piece. And so from here, now you use the abstract nonsense before, and now you have an honest to goodness differentiable Pimsner construction for Hermitian line module with Hermitian line connection. On the one hand, you can start from one of these, principal U1 pre-C-star algebra over B with horizontal calculus. You can spit out the the associated line with associated line connection of Chern number -1, or whatever your convention you want to take. And this will completely determine what you started with up to natural isomorphism. And conversely, you can start with the Hermitian line, with the Hermitian line connection, and then you can reverse engineer the unitary frame, quantum unitary frame bundle and the underlying quantum principal connection up to natural isomorphism. And so again, what happens when you take a single differentiable automorphism, consider the single trivial twisted Hermitian line module with its canonical flat connection induced by phi. What happens when you sort of apply this Kuntz-Pimsner construction? Well, you get the usual obvious flat calculus on the cross product. So before I talk about total calculi, I want to say something about curvature. So let this now be the usual Picard group, differentiable Picard group of isomorphism classes with respect to the monoidal product. You can make sense of the curvature of an isomorphism class. This will be the unique two-form F that satisfies this condition. So namely, nabla squared sub E of little e will be given like this. And so when you're starting with an automorphism phi, like all those twisted trivial lines are flat. They have curvature of 2 form 0. And so what's striking is that if you know the curvature 2 forms of the associated lines, you know this should be d sub p horizontal squared here. You know the square of your horizontal covariant derivative. And this means that this is not to be taken too seriously. This absent the requirement that anything squared to 0. This is not squared to 0. It in general is squared to something non-zero, and that non-zero thing is this curvature here. The joys of working last minute. So now I want to end this little section by starting to talk about something that I think has been coming up in a lot of the Prague group's sort of work on these relative line modules. So it turns out that there's something to be learned from looking carefully at the quantum Bianchi identities paper of Begsamidjid. There's unique homomorphism phi hat. So first off, let's remember that we have these Fröhlich automorphisms that live to the differentiable sort of setting. There's a unique group homomorphism from the differentiable Picard group to the automorphisms of the basic forms that commute with B that satisfy this condition. And now, so it's basically the generalized braiding on a Hermitian line induces in this way this automorphism. And now what's striking is that if you now want to think sort of about how curvature interacts with taking tensor products, it's actually, curvature is a one cocycle. It's an honest to God literal one cocycle. It's a one cocycle. It's a literal one cocycle for the action of this differentiable Picard group on this abelian group of an additive group of 2 forms on the base commuting with B with respect to the group action defined by this homomorphism phi hat. And what does the one cocycle condition look like here? It looks like this. This is what Begsamidjid observed. And this will be very, very important for us when we think about how to stack things together and actually get the total calculus now. So now I want to go talk about piecing together total calculi. So from here on, let kappa be a given non-zero real number. For n an integer, let the kappa number n be n if kappa is equal to 1, and otherwise the usual kappa number, non-symmetric kappa number. I take this choice because this is a cocycle in the one cocycle in the appropriate sense. Let's define a graded star algebra, a lambda sub k, basically of U1 invariant forms on U1. We'll have a skew adjoint generator d sub kappa of t that squares to 0. And now, given any graded U1 equivariant star algebra omega, let's define lambda sub, let's define this, this is supposed to be suggestive of some sort of smash product. It's supposed to be suggestive of the presence of some sort of braided structure. We'll define this sort of smash product, or whatever you want to call it, by saying, okay, let's take the naive Z2 graded tensor product of lambda sub, graded tensor product of lambda sub k with omega, and we'll mod out by these braided commutation relations. And this sigma sub kappa is supposed to be, that's supposed to be kappa to the power minus degree of omega. Kappa to the power minus degree omega. Those are the braided commutation relations that super commutation relations that you now impose, where we now define this d sub kappa of t to be U1 of 1 invariant. So now, given just a principal U1 pre-C star algebra, we can make sense of its kappa vertical calculus. We can sort of tentatively start trying to think of it as a differentiable principle U1 bundle with respect to the U1 with the funny kappa deformed differential calculus. And so what do? We just take P, throw in this d sub kappa t with the braided super commutation relation, just a commutation relation, and then we define the relevant vertical derivative like this. And when kappa is equal to 1, this is literally a Durham sort of naive differentiation. So now here's a workable definition of quantum principle U sub kappa 1 bundle. So we want to make sense of a differentiable principle quantum circle bundle with respect to this kappa deformed bicovariant calculus on U1. So what does this look like? We'll have a principal U1 pre-C star algebra P with this given identification of B with the U1 invariance. We'll have a U1 equivariant honest star differential calculus where the derivative of squares to 0, together with an isomorphism iota hat sub P, extending iota P, of the calculus on B with the U1 invariant part of the calculus on P. And then what we need to be able to do is have a well-behaved notion of what this thing represents is restricting total differential forms to the vertical tangent bundle, morally speaking. And what this represents is evaluation of a total differential form on a single fundamental vector field. So you have these sort of structure, you have these associated structure maps that are required to be well defined and have the appropriate kernels that let you isolate in the appropriate way what you mean by the horizontal forms. And so now you can talk about strong connections at this level of level of generality in terms of having a higher dimensional differential calculus. We could have had a strong connection on one of these quantum principle U sub kappa of 1 bundles to be an equivariant morphism of a U1 equivariant morphism of P star bimodules pi from the 1 forms to the 1 forms. That basically does the following. The identity over P extends via pi to an idempotent onto the kernel of this map that takes total forms and restricts them to the vertical tangent bundle. Restricts them to vertical forms. And conversely, if you extend the identity via the identity on the 1 forms minus pi, you get an idempotent of the entire algebra onto the what you want your horizontal forms to be. And so, as an example, the prime example, this is later on going to be checked, but starts with Brzezinski Majid. These finer points are going to be checked at various stages. The Q monopole on SU2 is a strong connection in this sense. So take SUQ2, with the 3-dimensional calculus of Vodonovich. The Q monopole is a certain canonical strong connection on the 3D calculus over Podlesh with its usual calculus of classical dimension due to Polish. So what I should impress upon you is that these definitions, these are all, this, like checking any of this it seems pretty ghastly. And so one thing I've been trying to propose with mixed success is that you can replace all these miserable considerations you can obviate a lot of this misery by really focusing on the factorization to vertical and horizontal pieces. So to do that, let's package together strong connections and quantum principle use of kappa of 1 bundles into just a category of invertible arrows in the obvious sort of way. And let me now point out that you can now take one of these total calculi with strong connection and spit out a horizontal calculus in an obvious way. Basically, you cut down d sub p via, this should be identity minus pi. You have this projection onto, this should, or horse of pi if you like. You have this, you can project onto the horizontal forms. Therefore, you can use that projection to define a horizontal covariant derivative. And so the goal for the rest of most of the rest of the talk is to exploit this now to get a differentiable Pimsner construction for total calculi. And so this is where curvature becomes all important. Let's say that a horizontal calculus is kappa adapted. Remember, we had this parameter kappa, non-zero kappa. It's kappa adapted if we can write the naive curvature, the covariant horizontal derivative squared, as the application of some U1 equivariant morphism of, we can factor it like this, basically as a vertical differentiation followed up by a vertical 1 form valued horizontal 2 form. That's what this is. And then you can form the corresponding strictly full subgroupoid of kappa adapted objects. And now the point is that you can identify precisely the range of this process of taking a total calculus and spitting out its horizontal part. Those horizontal parts are precisely the kappa adapted horizontal calculi. And you can reconstruct any total calculus from its horizontal calculus up to natural isomorphism. So this is the first step. So we can reduce the study of, they can completely reduce the study of total calculi for principal use kappa of 1 bundles to these horizontal calculi that are kappa adapted, and you can explicitly write down what this reconstruction looks like. And so this now lets us talk about differentiable Pimsner. Because now that we only have to worry about the kappa adapted horizontal calculi, you can precisely identify which bar homomorphisms arise as association of lines to a kappa adapted horizontal calculus. These will be precisely the bar homomorphisms whose curvatures satisfy this cocycle identity, one cocycle identity with respect to powers of kappa, negative powers of kappa. And then if you say, okay, let's move on to the generating Hermitian line with Hermitian line connection. What do the generating lines and with line connection of these particular things look like? Well, these are precisely the Hermitian lines with Hermitian line connection, satisfying the following. They're the Hermitian lines with Hermitian line connection, whose curvature 2 form is an eigenvector for its Völlig automorphism with eigenvalue kappa inverse. On the nose, that's exactly what it is. And so these particular Hermitian lines with Hermitian line connections are going to be precisely, ultimately, the Hermitian lines with Hermitian line connections you want. So this is now your differentiable Pimsner. In this particular case, basically, these total calculi with strong connection can be identified vectorially just with these particular special Hermitian lines with Hermitian line connection. And so this has various sort of implications. On the one hand, you have the usual sort of Pimsner idea of you know that you can start with something here and uniquely generate the appropriate total calculus ultimately up to natural isomorphism. But this also says something else. There's a fundamental obstruction to being able to take a Hermitian line module with a Hermitian line connection and build it up to a total calculus with a particular vertical, with a particular bicovariant calculus in the structure group, with et cetera, et cetera, et cetera. This kappa here is actually determined by the behavior of the curvature two form of the generating line with respect to its photic automorphism. This is so the moment that this curvature is non-zero, there's at most one kappa that does the job. So the vertical calculus you take, the calculus in the structure group that you take is actually, the moment you're not flat, it's actually determined completely by your Hermitian line with Hermitian line connection itself. And so what I love for folks to be able to do is to generalize all this to your favorite irreducible quantum flag manifolds. Let's consider the Q monopole over Podlish again. If we take the horizontal part of Voronov, the 3D calculus with the Q monopole, and do the associated line construction, we recover our usual relative lines with unique left SUQ2 covariant right connections. You look at the curvatures, they satisfy this one quacycle condition with respect to these negative powers of Q to the -2. And so in particular, at the end of the day, each of these curvatures of these, the curvature of curly E sub M is this Q sub -2 number times the curvature of the generating line. So this is the ultimate structural explanation for these phenomena you've been observing, and I'd be keenly curious to see to what extent they generalize to relative lines over more general irreducible quantum flags. So if I have time, I'd like to mumble very, very quickly about the question of encoding something like this Q monopole in terms of a U1 equivariant spectral triple. So this is an important technical definition that I literally did not have time to write up, so I'll just have to, unfortunately, take that on faith. But let me try to be reasonably precise about the problem I want to say. I don't even want to presuppose we have spectral triples. I want to look at the more basic question of being able to take a bounded representation just of the one forms compatible with a B bimodule structure on a Hilbert space and lift it in a structurally reasonable sense compatible with the theory of principal U1 spectral triples as initiated by Dombrowski and Ćaćić and completed and subsumed by work with Bram Mesland. I want to talk about this. I just want to talk about lifting the, if you like, the Durham sort of representation. So remember, we have B with a differential calculus, omega sub B. Let's define a Clifford representation of omega sub B to be a faithful star representation of the algebra B on a separable Hilbert space H, together with an injective star-preserving B bimodule homomorphism pi from the one forms on B to the bounded operators on H. So for, in particular, an important example, we'll say a spectral triple for B, whatever that is, spatially implements this calculus, at least the first order, whenever this formula here defines a Clifford representation of omega B. And in that case, we call this Clifford representation the Clifford representation induced by the spectral triple. So famous example, there's a spectral triple due to Dombrowski and Ćaćić that gets subsumed into this more general theory of the non-commutative Kähler calculus of irreducible quantum flag manifolds that famously spatially implements the canonical sort of classical dimensional calculus of Podlish for the Podlish sphere. So we can now completely generalize the notion of a metric continuity identified with Belisau, Marcolli, Rehani to this setting. We can say that one of these bar homomorphisms from Z to these lines with line connection is equicontinuous when it satisfies this condition here. And by the way, looking at the background here is this infamous fact that the R tensor product is lovely in all sorts of ways, but it's not invariant. Like there's something weird when it isn't necessarily well behaved when you flip the order in a tensor product. So there's sort of some fundamental issues with the order of tensor product that are lurking in the background here. And what this is saying is that those issues are sort of are pointwise uniform and not too bad. So if we know what equicontinuity is for these bar homomorphisms, then we have all these functors that let us, these equivalences of the categories that let us say what equicontinuity of a horizontal calculus is, what equicontinuity of a line with line connection is, what equicontinuity of a total calculus with strong connection is. And so if you just think about cross products by an automorphism, what is equicontinuity here? Well, it is literally, if you want equicontinuity with respect to Clifford representation of your basic forms, what is it? This is literally the condition of Berisha, Marcoli, Rehani. What's maybe more striking is that your Q monopole is not equicontinuous with respect to the Clifford representation of the Podlish calculus on the Podlish sphere with respect to that canonical spectral triple. And so the technical definition that I owe you of what I mean by a bounded lift of a Clifford representation with respect to a total calculus with module connection, but it's basically a minimalistic definition that would be automatically satisfied the moment you had anything vaguely. So basically a suitable U1 equivariant representation of the total forms. Bob, you can write down this definition. Unfortunately, I didn't have the time in either sense, but there's a natural definition that generalizes what you would need for spectral triples to make sense for any of this. And what you find is the following. Suppose you have a Clifford representation of the base. Suppose the kappa is positive or non-zero, really, it doesn't matter. And suppose that you have a total calculus with a strong module connection with respect to U kappa 1. Then you can lift, whatever that means, you can lift this Clifford representation up to here in a consistent sense that's consistent with the U1 action, et cetera, et cetera, et cetera. It's consistent with the business of restricting downstairs on the invariant piece to here. This admits a bounded lift. If this admits a bounded lift, then you have the following inexorable conditions. This is Kraft, H pi will be bounded, fine. You can finesse this to account for an unbounded Clifford representations as well on a common core. But what's more interesting is that this thing you started with, this total calculus with strong connection is forced to be equicontinuous. And not only that, but that kappa is forced to be 1. So you can only lift when you are in this sort of Derham equicontinuous regime. And so the Q monopole fails on both counts for the Clifford representation of the base induced by this canonical spectral triple. You have this Q squared, which is very much not equal to 1, but you also have a failure of metric of this equicontinuity. And so what this suggests is that the Q monopole is completely outside, and even worse, this Q squared, the powers of Q squared in the vertical direction are different from the powers of Q in the horizontal direction that you see from this failure of metric equicontinuity. So there's no way to encode, to lift the spectral triple of a Podlish upstairs to SUQ2 in a way that really respects the Q monopole structure. So last thing I want to mumble, if you are equicontinuous and if kappa is equal to 1, then you can go to town with principal U1 spectral triples and everything works out fine. So that I'm way over time. Thank you for your patience and indulgence. And that's all, folks.
Thank you very much. Do we have any questions in the audience? Andre, go ahead.
Yeah, I have very naive question and sorry for ignorance, but these kappa guys, do they have something to do with length spaces? And, you know, instead of considering sphere, I consider some kind of a weighted sphere.
This, I feel like in the kind of examples you're looking at, usually the kappa and sort of both the kappa that you need. And so remember, this, the moment you're dealing with line modules that aren't flat, kappa, if it exists, is completely and utterly forced upon you. And now the thing is that this thing is, and the kind of examples you're probably gunning after, this homomorphism is coming from this generalized braiding, and the generalized braiding in turn is going to be a creature of the braided tensor category that's floating around in the background. So if that braided tensor category is involving some particular Q and its powers, then you're probably going to see that Q there, but I don't know what more I can say. I don't know if that makes any sense.
Okay, maybe I kind of reformulate it in a very strange way. That instead of, for example, sphere as a total space of some sphere bundle, I should consider something weighted like this, length spaces and stuff like that, Firefox spaces. Because then probably this kappa will refer to the weighting. Well, again, it's very naive.
It would be interesting. It would be super interesting. Like, so like at the end of the day, like this kappa is a creature of your line and its generalized braiding. It's if you like, it's a numerical, like it's some sort of numerical invariant of this thing. So whatever it looks like, however it works, like I don't know. Like, it would be interesting. Like and already, I guess in some of the recent papers of the prog group, like you have these sort of more.
Yeah.
There have been some calculations of these things starting to appear.
Yes, for projective guys.
Yeah.
Okay, great. Thanks.
Other questions? Edwin, you look like you have a question.
Oh, yes. Thank you very much. That was a very good talk. I mean, actually, but just on this page, is it in general possible that kappa might not necessarily be a constant, but could be some other central element?
That you could finesse this. You could finesse this. So let me look at the right place. If you look at the where do I want? Not kappa adapted. I want to look at you can, this thing means that you could, like, for instance, you could take something like fix a non-commutative symplectic form and look, then you'll actually have a subgroup, an actual subgroup of the differential Picard group of isomorphism classes of lines with line connection, whose Fröhlich automorphism applied to the symplectic form is some central thing times the symplectic form, and such that the Fröhlich automorphism applied to the curvature is also some central, and such that the curvature is some central thing times the symplectic form. And that will give you a subgroup, and that's something that you could penetrate. That then you'd have these kappas that get that, as you point out, you have kappas floating around that would not be constants, but they'd be invertibles. And yeah, in that case, here, I mean, you could start playing these games. You could finesse. If things were, if with enough hypotheses, you can finesse this here, and what you'd end up with, if you can get away with a single non-constant kappa, then like you're sort of dealing with some sort of basically varying family of orbit-wise calculi. And in the Riemannian spectral triple setting, this is something like in terms of spectral triples in the de Rham case, in terms of just the Riemannian situation, having an orbit-wise sort of central sort of length function. That's something that's already appeared in Dąbrowski-Szytaj and the work with Rham. So yeah, there's lots of room for kappa to be non-constant.
Thank you.
Other questions? Ray, you look like you have a question.
Hello. Yeah, so thanks, Branimir, for a very interesting talk. It's very nice to see some kind of conceptual explanation of the curvature, the cuneiform curvature. So can you remind me, what exactly do you need to make this work? Because I'm trying to see if this can be extended.
Okay, so what would the cookbook have to be? So this sort of mystery here, there's a lemma in Begg's in the Quantum identities paper. Like if your basic calculus is the maximal prolongation, then you can finesse this considerably and simplify this down considerably. So then it becomes relatively easy to get this, relatively easy to guarantee that the existence of a sigma E, of a sigma that satisfies the appropriate properties and the satisfaction of the left Leibniz rule and this complete generality. From then, what you need to know. So okay, in the cases you're interested in, then the lines you care about. Actually, one thing will help you immensely is that the lines you care about you're always dealing with a Turing connection whose curvature is a scalar multiple of some fixed symplectic form you care about. And that symplectic form will be central, so that helps you considerably. So what do you ultimately need to know? You need to know what Fröhlich does to your symplectic form.
Mm-hmm.
That is all important. This is the most important single computation in that case. Determining what this Fröhlich actually really just in that case, if you're just considering starting with a single line and sort of taking powers, you just need to know, you just need to look at your generating line, which is whatever non-zero scalar multiple of your symplectic form it is, and see what that generated Fröhlich homomorphism does to the symplectic form.
So it's going to map it into, okay. Okay, I mean, because basically, so for the irreducible flags, we have a calculus upstairs that generalizes more or less the, well, it generalizes, I guess, the horizontal part of the Voronowicz 3D calculus, but I mean, the vertical is not so important. And that gives you a quantum principal bundle describing the Heckenberger code, so probably it should work. I mean, the curvatures of the line bundles for these things are, the curvature of the line bundles for these things are definitely Q integers as well. I mean, this we can show. It's not written down.
So if you know which Q integers,
they're given in terms of, there are going to be some powers of Q given abstractly in terms of an R matrix.
So that's an interesting. So then the question becomes, how does that R matrix? How do the resulting powers behave? Like, will it just boil down to powers of some funny power of Q?
Yes, that's exactly what it would.
If it's just powers of some funny power of Q, then it looks like you're staring this condition in the face.
Yeah, that would be what would happen. Yeah.
So that is equivalent to saying that the generator satisfies with that. Then that would imply that this condition that would be equivalent to this condition, the generator.
Okay.
And then the other thing is that funny power of Q that you have, like that is now going to be the only kappa that gives you a reasonable total calculus that makes everything work. So actually, one of the upshots is that you have very, very strong uniqueness results. So for instance, one of the upshots is that the 3D calculus is the only left SUQ2 covariant principle, blah, 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 that lifts the published calculus and published in a manner compatible with the Q monopole.
But if you take the 3D calculus, then you can quotient out the vertical part and get a two-dimensional calculus.
That's a horizontal calculus.
Yeah.
That's just the horizontal piece.
The horizontal piece. So basically what we have in general, what Eckenberger and Cole produced in general for the irreducible flags is basically a horizontal calculus. There's no vertical part. I mean, I guess you could add it in.
So I guess one of the things is that if you know the horizontal part, you can go through this process. And the moment you have a formula like this with a kappa, or in the moment you have a formula like this with some kappa, then that's your God-given kappa to complete the calculus. And life is good.
Okay.
But then if you want spectral triples, there's this uncomfortable fact here that the moment kappa is not equal to 1, you're dead into the water. And the moment, let's say you're dealing with powers of q, the moment you have one power of q in the vertical direction, specifying the orbit-wise calculus, and a different power of q governing the failure of equicontinuity, you can't even use twisted spectral triples. So that we're really dealing with the sort of the outer limits of the extreme outer limits of the spectral triple formalism, even the twisted spectral triple formalism as we know it.
Okay, and can I ask just a reference question? The results there from Shannon Edwin that you cited with the foolish map, where is that in the book or it's a paper?
Biggs Magenta 18, that's the quantum Bianchi identities paper.
Quantum Bianchi identities paper. Okay. So yeah, maybe I should have a look at that. No, so yeah, okay. Thank you.
All right, any further questions? Let me just have a look through the audience. Looks like we're all in the clear. So let's thank Branimir again.
Okay.
You're up, Branimir. And next week, we have a live performance on essential groupoid C-star algebras of non-Hausdorff groupoids from Jonathan Taylor at the University of Göttingen. So hope to see some of you in person and online next week.